Okay, write the equilibrium expression for each of the following reactions. So, equilibrium expression. This is chapter 7 material. That's where we talked about equilibrium, and the expression for equilibrium is our expression for the equilibrium constant K. Okay? So here it doesn't say to solve for K, it just says to write the expression for K. We don't have any numbers, so we can't plug anything in and solve. Also, remember here, we do not include, I'm going to write this out. Don't include solids, anything that's a solid, or anything that's a pure liquid. Okay? This is because the concentration of these, the amount doesn't change as you increase or decrease amounts based on set concentrations. And the understanding of this is really kind of beyond the scope of this class, so just kind of take it at face value here that we only include things that are gases or things that are aqueous into our expression for K. So let's write it out for the first one here, number 1. Remember that K, I'll actually go down here to the bottom. Generically, K is the concentration of products divided by the concentration of reactants. And you raise them to the power of their coefficients. Okay? So for the first problem, we'll go back up here. Here's our product. It is a gas, so we can't include it. So it would be the concentration of NH3. Raise it to the power of its coefficient, which is 2. So we'll square it. Divided by, we have 2 reactants. They are both gases, so we can include them both. So it'd be, oh, I better do the first one first. It doesn't matter, really, as long as they're both there. But nitrogen, and this 2 on nitrogen, let me erase this here so you can see this. If I zoom in, this 2 on nitrogen, this is not a coefficient. So this is not telling you to square it or anything. You just have to write, it's part of the chemical formula. So that's why I'm writing N2 over here, okay? So don't mix up subscripts and coefficients. Coefficients are out front. I'm on eraser. Coefficients are out front, and this is what you raise to the power of over here. But subscripts are included in the chemical formula, and those don't change. So don't get confused by that. And these, I've seen that happen when people write these out. So I wanted to make note of that. We don't have a coefficient for nitrogen, so we don't raise it to the power of anything. Essentially, it's raised to the power of 1. But for hydrogen, H2, and our coefficient is 3, so we raise it to the power of 3. The exponent here is 3. Okay, and that's it. That's the expression for K for number 1. Number 2, we do have one thing that is a solid, so we are not going to include iodine in our equation here because it's a solid, so we won't include iodine. All right, but we will write concentration of products, so that's ICl, iodide chloride. Interesting compound here. And it's a gas, so we've written it and we square it because the coefficient is 2. And we'll write the concentration of the only reactant we're going to include, which is chlorine, or chlorine. And the coefficient is 1, so we raise it to the power of 1. You don't have to write that in. The 1 is understood. Okay, number 3. Everything in this equation is gas, so we'll include everything. So we have nitrogen monoxide, coefficient of 2, so we'll square it. We also have oxygen, coefficient is 1, so we leave it alone. And the only reactant we have is nitrogen dioxide. Its coefficient is 2, so we square it as well. And that's it for this problem. That is how you write the expression for the equilibrium for each of these reactions. Okay, next problem. For the reaction below, which change would cause equilibrium to shift to the right? Okay, so this is a Le Chatelier's principle. Okay, this is, again, chapter 7 stuff. We want to know what's going to cause equilibrium to shift to the right. Okay, so I'm going to erase so I have more room. I'm going to write all over this equation. If we're shifting to the right, we're shifting this direction. So we'll follow each of these scenarios. Let's start with A. If we decrease the concentration of dihydrogen sulfide, what is dihydrogen sulfide? H2S. And we are taking the concentration of it and decreasing it. So if we decrease H2S, remember equilibrium is going to want to shift in a direction that replaces whatever we take away. We're taking away one of the reactants. So equilibrium is going to shift towards the reactants in this case. So in actuality, I'll just keep the same color. In this scenario, equilibrium would shift left and not right. So A is not going to cause equilibrium to shift to the right. It would cause equilibrium to shift to the left. Okay, let's look at the second scenario. We're going to increase the pressure on the system in B. Remember when you're predicting how equilibrium shifts based on pressure changes, you need to examine how many moles of gas do you have on each side. Okay, so if we're looking at the reactant side, I have 1 mole of CH4 and 2 moles of H2S, so total that is 3 moles of gas. On the reactant side, on the product side, I have 1 mole of CS2 gas and 4 moles of hydrogen gas. That is 5 moles of gas. So we have a difference in the number of moles of gas, and if you increase the pressure, it will cause the system to shift to the side with the fewer moles of gas. If you increase pressure, then we're going to shift to side with fewer moles of gas, which is the reactant side. So that would cause a shift left. So B is not what we're looking for either. We want to know which thing's going to cause equilibrium to shift right. Okay, let me erase so I have more room up here for scenario C. Okay, on C we're going to increase the temperature of the system, and I don't think we have enough information to do this one. We need to know if this is endothermic or exothermic. Okay, so we actually don't know. We can't do C because we aren't told anything about delta H and whether heat is a reactant or product, and we would need to know that. So we can't do C. D, if we increase the concentration of carbon disulfide. Carbon disulfide is this right here, and we are going to increase the concentration of it. So that is a product. Here it is on the right hand side of the equation. If we increase the concentration of a product, Chatelain's principle says that we will shift back towards the reactant side. So we would actually shift left. Okay, so D, that causes a shift left, not right. So that's not what we're looking for either. Maybe it's going to be E. That's the last one we have left. If we decrease the concentration of methane, methane is CH4, so we are taking the concentration of it and we're decreasing. Methane is a reactant here. If we decrease the concentration of methane, that means we are, I never erased from the previous problem. We decrease the concentration of methane, we are going to cause a shift back towards the reactants so that we will replace the thing we take away. And that's going to cause a shift left. So, nope, it's not E. Maybe it would have been C, but we don't have enough information to actually answer that. Okay, that is it for this problem. So none of the above, in case you're wondering. All right.